Is the universe without end? I'm asked this question constantly, and the reply hinges on something we haven't entirely figured out yet. What's the total amount of matter present? What's the actual strength of gravity? But I can tell you what we do know and what the math predicts, because the possibilities are much stranger than you'd imagine. Space itself is expanding, even as we speak. Galaxies billions of light years distant are hurtling away from us at thousands of miles every second. Their speed increases with their distance. The space between them is stretching, it's growing. Each second, the universe grows larger. You won't perceive it. The effect is too minute in our local region, but it's undeniably real. And here's what this implies. Considering space's current expansion, it follows that in the past, all matter was more tightly packed, reversing the flow of time. Galaxies would converge, becoming denser and hotter. Continue this regression, further and further into the past. To what point? Until all existence, each galaxy, every star, every single atom, occupied a singular location, compressed into a form of unimaginable smallness and density. That precise instant, that genesis, it's what we refer to as the Big Bang. Not merely an explosion occurring within space, but rather the explosive expansion of space itself. The singular instant when all things originated. However, allow me to explain how we deduce this and its profound implications, for the consequences are considerably more astonishing than you might imagine. During the 1920s, celestial observers commenced examining remote galaxies, meticulously gauging their emitted light, and they observed a rather unusual phenomenon. The light observed wasn't precisely the correct hue. Its spectral signature showed a shift towards red, a clear case of red shifting. Now, one might naturally wonder, what's the significance? Light's hue, after all, is constantly in flux. This particular instance, however, proved distinct. The observed spectral shift adhered to a specific pattern. The greater a galaxy's distance, the more pronounced its light was observed to be redshifted, not by a small margin, but quite substantially. What, then, is the underlying cause? It's simply motion. When an object recedes from your position, its light becomes stretched, much like the sound waves from a car driving away. As it recedes, the sound's perceived pitch drops. The very same principle holds true for light. Motion elongates the wavelength, consequently making it appear redder. So space itself is expanding, a process underway since the very universe's inception. But here's the profound question that truly captivated my thoughts. What's the next stage? Will this cosmic expansion persist eternally? Or does some other event transpire? The solution rests on a singular principle, the force we call gravity. Every single thing across the cosmos possesses mass. The existence of mass gives rise to gravity. Gravity exerts an attractive force. Even as the fabric of space stretches, and despite galaxies are hurtling away from each other, gravity actively opposes this motion, striving to draw everything back into a unified whole. It's akin to the act of launching a ball upwards. The ball ascends, only to be drawn back by gravity's influence. Its ultimate return trajectory hinges on the initial speed at which you launched it skyward. Launch it slowly, and gravity inevitably triumphs. The ball ascends, loses momentum, momentarily pauses, then reverses its course. Now propel it with greater velocity. At a specific critical speed, what we call escape velocity, the ball just barely manages to break free. It continues its ascent indefinitely, yet its velocity gradually nears a standstill. Propel it with even greater speed. It effortlessly breaks free, continues its upward journey, never to return. The cosmos behaves similarly. All hinges upon a delicate equilibrium. The pace of cosmic expansion, weighed against the intensity of gravity's counterpull, this presents us with three potential outcomes, three distinct paths for the universe's narrative to conclude. The initial scenario unfolds thus. The cosmos expands with excessive rapidity. Gravity proves insufficient to adequately decelerate it. The universe will continue its expansion indefinitely. Galactic clusters hurtle away from one another. Ultimately, their separation grows so immense that light from a single galaxy can no longer traverse the distance to another. Each entity becomes solitary, adrift in a boundless sea of gloom. Stars extinguish their brilliance one after another. The cosmos becomes frigid, dim, and utterly vacant. The cosmos does not conclude with a dramatic flourish. Instead, it simply wanes, growing progressively colder and ever more desolate until no noteworthy events are able to unfold again for all eternity. Herein lies the second potential outcome. The spatial fabric extends precisely at its critical velocity. Gravitational attraction exerts just enough counterforce to impede its outward progression, yet not bring it to a complete halt. The cosmos continues its eternal expansion, albeit at a progressively reduced pace. Upon reaching infinite duration, the rate of expansion draws near to zero, maintaining a perfect equilibrium, as if on a razor's edge. Such is the flat universe, and its ultimate destiny bears a resemblance to the initial scenario. Perpetual outward movement, yet held in precise equilibrium at the critical velocity. The third potential scenario unfolds as follows. The spatial expanse fails to expand with sufficient rapidity. Gravitational pull proves excessively potent. The cosmic expansion decelerates, ceases, and subsequently reverses its course. Galaxies halt their outward retreat, commencing an inward approach. The very fabric of space initiates its contraction. All constituents draw nearer, growing increasingly dense and intensely hot. Envision the Big Bang event unfolding in reverse. Galactic structures impact and coalesce. Stellar bodies are violently disintegrated. Material substances undergo intense compression. The ambient temperature escalates. Ultimately, space shrinks to such an extreme degree that atoms are unable to persist. Subsequently, molecules and even subatomic constituents are obliterated. All existence collapses inward, converging into a singular point, a big crunch, the antithesis of the Big Bang's genesis. The cosmos, born from an inferno, ultimately concludes in flames. All that comprises reality is compressed back into what form? Perhaps a singularity once more. Conceivably, a subsequent Big Bang, or perhaps an entirely different outcome. That remains an open question. Which of these possibilities describes our own cosmos? Back in the mid-1960s, we simply didn't possess that knowledge. The resolution to this question rests on the total quantity of matter in existence and the actual potency of gravity, not solely considering the observable matter, stars, galaxies, and cosmic gas, but instead the whole lot, including the matter we cannot directly perceive. And as I was reflecting on this, particularly concerning the universe's expansion or potential contraction, a significant realization struck me. If the entire universe is capable of collapsing, then what about more diminutive celestial bodies? What then of individual stars? Stars exhibit remarkable stability, enduring for millions of years, even stretching into billions of years. They undergo hydrogen fusion. Nuclear fusion processes deep within their core release energy. Radiation pressure exerts an outward push. This effectively counteracts gravity's relentless effort to crush the star inward upon itself. However, nothing in the cosmos endures eternally. Ultimately, the star's fuel supply is exhausted. Its hydrogen reserves are entirely consumed. Nuclear fusion decelerates, then ceases altogether. The outward expansive pressure vanishes and gravity asserts its dominance. For stars of lesser mass, those akin to our own sun, this event unfolds with comparative mildness. The star cools, undergoes contraction, and transforms into a white dwarf, an Earth-sized glowing remnant composed of highly compressed matter, initially incandescent yet gradually cooling across trillions of years, ultimately transforming into a cold, dark sphere, a veritable celestial cadaver. However, for stars of immense mass, a distinct phenomenon unfolds, one that is exceptionally violent. Once nuclear fusion ceases within a massive star, its subsequent implosion proves catastrophic. The stellar core undergoes implosion within mere seconds. Electrons are forcibly compressed into protons. These particles then combine, giving rise to neutrons. The core transforms into a neutron star, a dense sphere comprised solely of nuclear matter, with dimensions comparable to a city's dimensions, yet containing the sun's entire mass. Its density defies all human understanding. Just 1 teaspoonful of neutron star material would weigh as much as an entire mountain. The gravitational force on its surface is so immense that, were you to release an object from merely a meter's height, it would strike the surface at a considerable portion of the speed of light. However, neutron stars possess a mass limit, approximately 1.5 times the sun's mass, known as the Chandrasekhar limit. Beyond this, they cannot sustain themselves. Exceed that boundary, and even the immense neutron degeneracy pressure is insufficient to support the star. What transpires then? The gravitational collapse persists. It is precisely at this juncture that phenomena become truly bizarre. My attention turned to a meticulous examination of the underlying mathematics, specifically the equations that delineate gravity's behavior around an incredibly massive compact celestial body. These, of course, are Einstein's field equations, the very core of general relativity. When we consider ordinary objects, planets, stars, even those dense neutron stars, the mathematical descriptions function perfectly well. They accurately foretell gravity's actions, how time itself progresses, and the very bending of space. However, if you compress matter past a particular density, something quite peculiar emerges within the calculations. It's a crucial dimension, a distinct limit. For any specific quantity of mass, a threshold exists beneath which the formulas foretell something utterly strange, a precise location where the math declares time simply halts, where space itself entirely folds in on itself. This phenomenon we term the Schwarzschild radius. It bears the name of Carl Schwarzschild, who uncovered this solution to Einstein's profound equations way back in 1916. Considering our Sun, this crucial dimension measures approximately 3 kilometres in diameter. For our planet Earth, it's merely 9 millimetres, a dimension comparable to that of a small marble. For absolutely any given object, one can compute this crucial radius. Its value is solely determined by the mass. As an object's mass increases, its critical radius expands. However, this critical radius expands at a slower rate than the object's actual physical extent. Thus, ordinary celestial bodies, stars, planets, are vastly distant from this critical threshold. Their physical dimensions vastly exceed their corresponding critical radius. Yet, if one were to hypothetically compress the Sun to a mere 3 kilometres in diameter, or the Earth to the size of a marble, one would then encounter this boundary. This pivotal circumference where the very mathematics ceases to make coherent sense. A locale where something profoundly peculiar transpires, an object having been compressed beyond its Schwarzschild radius. In essence, a star that has undergone gravitational collapse. That was the designation we applied to these phenomena in the mid-1960s period. Furthermore, some individuals also termed them frozen stars for reasons. The clarity of this will soon reveal itself, or, as some might call it, a black star, since no radiation can get out of their immense gravity. No matter the name, the theoretical outcomes were utterly peculiar. The most astonishing prediction, however, dealt with the experience of a person who tumbles headlong into one of these. Permit me to present a mental exercise. Let's set aside the intricate calculations momentarily. Simply picture this unfolding scene. A colossal stellar body is in the process of collapsing. Its very heart is violently imploding. The relentless grip of gravity is compacting it, making it progressively smaller. Now let's envision a person, an observer, situated right on the exterior of this star as it collapses, journeying downward alongside it, being drawn inward, accompanying its descent. Now suppose you are situated a great distance away, completely out of harm's way, gazing upon the event through the lens of a telescope. What then would be your observation? Initially, there's nothing out of the ordinary. The stellar body contracts, its size diminishes, its density increases. An observer positioned on its surface begins to fall inward. Photons emitted from that surface journey towards your telescope. You perceive their presence at that location. Perhaps they are signaling with a wave, or even performing a dance, transmitting messages via light. However, once the star nears its critical dimension, specifically the Schwarzschild radius, peculiar phenomena begin to unfold. The illumination emanating from its surface and reaching you undergoes a transformation. Its hue shifts towards the red end of the spectrum, and it becomes fainter. This effect is known as gravitational redshift. Electromagnetic radiation escaping a powerful gravitational well experiences a loss of energy. Consequently, its wavelength elongates, causing it to move towards the red spectrum. The greater the gravitational pull, the more pronounced the light's redshift becomes. When the star draws near its critical radius, the gravitational redshift reaches an extreme level. Yet, that is not the full extent. Even time itself undergoes alteration. The motions of the observer appear to decelerate. He makes a gesture with his arm. However, from your distant vantage point, that motion unfolds over a duration exceeding its normal span and even more protracted, still further extended. From his own viewpoint, nothing has changed. His arm gesture proceeds at its customary pace. His timepiece maintains its regular rhythm. Nevertheless, the light conveying that information to you is undergoing stretching due to gravity's influence. Its arrival is postponed. As the star draws ever nearer to its critical dimension, the observable effects intensify dramatically. From your vantage, the observer's motion progressively slows down. The light he emits shifts increasingly towards the red end of the spectrum and grows ever fainter. Ultimately, as the star attains its Schwarzschild radius, an extraordinary phenomenon unfolds. From your viewpoint, the observer comes to a complete halt entirely. He becomes fixed in position, much like a still photograph. His visual representation remains fixed at that demarcation line, perpetually descending yet never truly traversing the threshold. For him, time has ceased its flow, at least when viewed from your perspective. His emitted light is so profoundly redshifted that it's virtually imperceptible. He remains suspended at the periphery of this collapsed stellar body for all time. This is precisely why some refer to it as a frozen star. From an external vantage point, nothing can ever transcend that limit. Every process simply decelerates, becoming fixed in place. Yet, here lies the truly astonishing element. From the observer's vantage point, what then? What are his perceptions? Absolutely nothing. Utterly devoid of experience. His perception is that time flows as usual. He himself experiences no deceleration. No unusual phenomena are apparent to him. He traverses the critical boundary known as the Schwarzschild radius straight across its threshold. No forewarning whatsoever, no discernible marker, neither a sudden jolt nor any break in continuity, simply a fluid, unbroken movement towards the interior. In his perception, it occupies perhaps a mere handful of seconds, a minute, or indeed any finite span of time. The boundary is crossed by him completely unnoticed. Nonetheless, once that threshold is breached, a transformation has occurred. An attempt is made by him to dispatch a signal, a radio signal, a ray of light, or any other form of communication, yet it proves ineffective. The issue isn't a block transmission, but rather that the very fabric of space is so profoundly warped close to the collapsed stellar remnant that all vectors point solely inward. An outward trajectory ceases to exist. Every conceivable route, each potential course, draws one further into the star's core, towards its very heart. One finds oneself ensnared. Communication becomes impossible. Escape is unachievable. Sending a distress signal is futile. From the individual's viewpoint, the descent is continuous, ultimately arriving at the core where gravitational stresses grow boundless and all matter is utterly pulverized. At that point, our mathematical models fail. The true events remain beyond our comprehension. An external observer perceives him as perpetually suspended at the event horizon. Yet from within, the passage through occurs in a finite duration and is destined for an inevitable end. Both portrayals hold validity. These are merely distinct viewpoints concerning the identical underlying physical reality. For time itself progresses at varying rates across diverse locations. In the vicinity of powerful gravitational fields, time's pace slackens compared to observers situated far away. Furthermore, at the Schwarzschild radius, when viewed from an external standpoint, time effectively ceases. While this may strike you as science fiction, it is quite real. Indeed, time genuinely progresses at disparate speeds within diverse gravitational environments. We have empirically confirmed this. Your head actually ages more quickly than your feet do. Currently, the disparity is minimal, yet it's precisely measurable. Your head is situated a little further from the Earth's core. The gravitational force is marginally diminished at that point. Thus, time progresses a little more swiftly. Across the span of your whole life, your head will have aged an additional 90 billionths of a second beyond the duration experienced by your feet. It's imperceptible to us, yet undeniably true. Only a short time ago, in 1960, physicists performed an elegant experiment, the Mossbauer experiment. Researchers employed a photon, a single quantum of light, which they then dropped 24 meters from the summit of a tower down to its base. Its frequency was then measured once it reached the bottom. A change, a definite shift in frequency occurred because the photon descended from an area where time progresses marginally more rapidly into a region where time proceeds somewhat at a reduced pace. This alteration was minuscule, merely 1 part in 1,000 trillion. Yet they successfully measured and verified it. It is true. Time truly flows at disparate rates. In the vicinity of a neutron star, this phenomenon becomes quite pronounced. On the surface, time might progress at merely half the rate as time observed from afar. A single hour spent in that location equates to 2 hours for remote onlookers. Furthermore, in proximity to the Schwarzschild radius of a collapsed stellar body, time, when viewed by a far-off observer, practically ceases. A single hour experienced by the plummeting observer could correspond to billions of years, indeed infinity from a technical standpoint, for remote onlookers. Consequently, the observer in freefall seems to be suspended in time. From his personal viewpoint, he is certainly not motionless. However, time progresses so divergently for him that from your vantage point, he might as well be entirely halted. The Earth's central core is chronologically younger than its outer crust by approximately 2 days due to time's decelerated passage deep within Earth's more intense gravitational field. Across a span of 4.5 billion years, this accumulates to roughly a 2-day discrepancy. This is not mere conjecture. It does not constitute a theory in the sense of perhaps. This is indeed true. Its existence has been measured and corroborated by the Mossbauer experiment, among other studies, rendering it as tangible as any other physical reality. Now, if these stellar remnants truly exist, how then would one go about detecting them? They emit no light by their inherent definition. Light is unable to escape from within the Schwarzschild radius. They are, in essence, invisible and dark. Voids in space where stars once resided. I've considered this particular problem, and it seems there are a handful of potential methods, all of them indirect, all of them challenging, but nonetheless feasible. Let's begin with binary star systems. Most stars you see are not solitary. They often have companions, a pair of stars revolving around their mutual center of mass. Now, if one of these stars collapses, becoming one of these black stars, you would observe something quite peculiar. A visible star seemingly orbiting a void, though it is not in fact truly empty. This observable star is being drawn by something, a colossal unseen entity. One could meticulously track the visible star's trajectory, map its orbital path, then deduce the heft of its unseen partner must possess. Now, if that mass surpasses the Chandrasekhar limit, if its bulk is too great for a neutron star, and if this entity remains dark, then perhaps you've stumbled upon one, a collapsed star. Indeed, this stands as one of the more hopeful approaches. Numerous stars exist within binary arrangements. Should collapsed stars truly exist, some of them are bound to possess observable partners, and we ought to be able to discern their gravitational influences. Next up, gravitational lensing. Light paths curve when near massive bodies. Einstein foresaw this phenomenon way back in 1915. The sun's gravity warps starlight. We quantified this effect during the 1919 eclipse. It validated Einstein's predictions. A star that has undergone collapse would warp light to an even greater degree, quite profoundly. Should radiation from a far-off star travel close to one of these, its path will curve. This collapsed stellar remnant functions as a gravitational lens. Given an ideal alignment, the collapsed star, with a remote star positioned directly behind it, and your own observation point, you could potentially witness the radiation from that distant star curving around the collapsed object, appearing distorted, perhaps as multiple distinct images, or even forming a luminous ring of illumination. The likelihood of achieving such an impeccable alignment is quite low. It necessitates the precise positioning of the collapsed star, the star in the background, and your observational instrument, all to be perfectly collinear. While the chances are exceedingly poor, they are not entirely non-existent. It's a scenario of extreme improbability, yet it remains within the realm of possibility. Such an event might become observable one day, provided we examine a sufficient quantity of stars and capture an adequate number of photographic plates. Ultimately, sheer chance could bestow upon us the precise alignment required. Around the mid-1960s, several of my fellow researchers I encountered notions concerning collapsed stars which I considered unsatisfactory. A prevalent hypothesis asserted that stars are simply unable to contract past the Schwarzschild radius. They are incapable of turning into these frozen stars or black celestial bodies. Some inherent mechanism must exist to prevent such an occurrence. The line of reasoning unfolded thus: should a star surpass the Chandrasekhar limit, it will undertake some action to avert a complete collapse. It will detonate, shedding mass in a supernova event, anything to fall beneath that threshold. For if it failed to do so, it would persist in collapsing beyond the Schwarzschild radius, and no one truly wished to contemplate the ultimate destination of such a path. However, this troubled me, for it fails to elucidate the underlying reason for stellar explosions. It merely posits they explode because they are compelled to avert a collapse. That represents circular logic. It's akin to asserting that divine intervention triggers supernovas, thereby allowing us to sidestep concerns regarding stellar collapse. Such an explanation isn't scientific inquiry. It merely sidesteps the fundamental inquiry. A different perspective, which I playfully dubbed the all-right Jack theory, posited the following. One cannot observe what transpires within the Schwarzschild radius. It's impossible to forecast the occurrences in that region. Our mathematical frameworks cease to function at the singularity. Therefore, why should I trouble myself with it? Provided I remain secure outside, everything's all right, Jack. This viewpoint genuinely troubled me, for the infalling observer confronts a genuine predicament, a tangible future, a definite destiny. Merely because we lack external observation of it doesn't render it unreal. Nor does it imply we ought to disregard it. The inquiry into what transpires within is intricate, exceedingly complex. The underlying mathematics proves challenging. Our physical intuition proves inadequate. However, evading the inquiry is not the solution. This argument rather circumvents the core issue by failing to provide any answers. Should physics predict something peculiar, something disquieting, we are not at liberty to disregard it simply because it's inconvenient. We are compelled to ponder it, to delve into it, to strive for its comprehension, even if the conclusions prove peculiar, even if they are disquieting. Such is the very essence of physics. The inquiry presents a complex challenge, and it certainly warrants careful consideration. Consider the events unfolding at this very moment. Somewhere within the cosmos, an immense star undergoes collapse, its fuel supply exhausted, gravity relentlessly compressing it, making it ever smaller and more compact. And should its mass be sufficient, should it exceed that crucial threshold, its collapse will be unstoppable. It will continue its collapse past the Schwarzschild radius, beyond the critical point where even light cannot escape. From a great distance, an onlooker perceives it slowing down, then freezing. The star appears to halt its motion at the boundary, permanently immobilized there. From their viewpoint, time itself has ceased to flow. However, an observer situated on that star experiences nothing out of the ordinary. They traverse the boundary in mere seconds or minutes, experiencing normal temporal progression. If they then try to signal outward, they find they cannot. They are utterly trapped. Space itself has curved with such profound completeness that every direction now leads inexorably inward. Both sets of observers are, in fact, correct. Time genuinely flows at different rates for each of them. This is not a philosophical conjecture, it is an empirical measurement. The Mossbauer experiment provided the conclusive evidence. When a photon falls a mere 24 meters, its frequency is observably altered. Your head actually ages more quickly than your feet do. The very core of our Earth is, in fact, younger than its surface. We all understand that time moves forward, yet you must truly pause and reflect upon it to genuinely grasp the profound implications. Time, you see, isn't uniform across the universe. It warps, it stretches. Close to powerful gravitational fields, its passage can nearly grind to a halt. But what about space itself? The very fabric of space is expanding at this moment. Galaxies are hurtling away from each other. We can quantify this, observe it directly in the redshift of light from distant celestial bodies. If you were to reverse time's arrow, everything would collapse into a singular point. That, of course, is the Big Bang. Let it run forward and perhaps space will continue its expansion indefinitely. Perhaps at some future point everything will recollapse. This remains an open question. Separate stars undergo collapse. Conceivably, the entire cosmos could collapse. Alternatively, it might continue its eternal expansion. All these scenarios are predicted by the underlying mathematics. These are peculiar phenomena. These are unsettling concepts. However, mathematics is entirely unconcerned with our comfort. Its sole purpose is to delineate reality as it stands. Certain individuals prefer to sidestep these inquiries. They contend that stars cannot undergo such extensive collapse, insisting they must detonate beforehand. Alternatively, they might suggest we ought not to concern ourselves with what transpires within, given our inability to directly observe it. However, such an approach is not true physics. That amounts to an evasion. The inquiry itself is quite intricate. The underlying mathematics proves challenging. Our innate understanding proves insufficient. Yet, the ultimate resolution, whatever its form, possesses genuine reality. The individual plunging inward faces an undeniable destiny. Indeed, from a particular vantage point, time genuinely halts, even as it marches onward from a different one. These phenomena are not paradoxical. Both states of affairs hold true simultaneously. Therein lies its truly unfathomable character. The very fabric of space stretches. Temporal flow curves. Luminous stars succumb to the void of darkness, and our grasp of what all this truly implies is merely in its infancy. When one genuinely contemplates these ideas, truly pauses to absorb the pronouncements of the equations, then the cosmos reveals itself as vastly more peculiar than its outward semblance suggests. It is not a simpler reality, but rather a more profound truth.